In 2003, the Hubble Space Telescope pointed at a patch of sky so empty it appeared to contain nothing. After 11 days of continuous exposure, it resolved nearly 10,000 galaxies, each one 100 billion stars, each star a sun, and every single one of them moving away from us, accelerating. In 1998, two independent research teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other the Heisey Supernova Search Team led by Brian Schmidt with Adam Rees analyzing the data, discovered that the expansion of the universe is not slowing down. It is speeding up. Something is pushing it apart. We have named that something dark energy. We do not know what it is, and depending on its exact properties, it will determine how everything ends. In this video, we are counting down 10 scientifically grounded scenarios for the end of the universe. These are not science fiction. They are drawn from peer-reviewed cosmology, particle physics, and thermodynamics. Some of these endings are so far in the future that the number of years cannot be written in standard notation. One of them is something that, in principle, could happen at any moment. Though, as we will see, the physics gives us strong reasons to think the wait is extraordinarily long. We will start at number 10 and work down to the single scenario that is driven by the one piece of physics we have actually measured: dark energy. Let us begin. Number 10. Proton decay. The atom may not be eternal. Inside every proton, inside the nucleus of every hydrogen atom in your body, in this planet, in every star, there is, according to certain theories, a clock running. Grand unified theories, a class of models in particle physics that attempt to unify the strong, weak, and electromagnetic forces, generally predict that protons decay. The predicted timescale varies by model, but typically falls around 10 to the 34th years or longer. For context, the current age of the universe is roughly 1.38 times 10 to the 10th years. Proton decay has never been experimentally observed. The Super Kamiokande detector in Japan, 50,000 tons of ultra-pure water surrounded by about 11,000 photomultiplier tubes, has been searching for it since April 1996. It has not found a single confirmed event. The current lower limit on the proton lifetime, depending on the decay channel, is around 10 to the 34th years. This either means proton decay is extremely slow or these particular models are wrong. If protons do eventually decay, then on timescales so vast they resist ordinary comprehension, every atom of ordinary matter will dissolve. No stars, no planets, only radiation drifting through an expanding void. Number 9. False vacuum collapse. The quantum field that gives particles their mass, what physicists call the Higgs field, may not be in its true lowest energy state. It may be sitting in what theorists call a false vacuum, a local minimum, stable enough to persist, but not the deepest possible configuration. After the Higgs boson was discovered at the Large Hadron Collider in 2012, two influential calculations, deGrasse and collaborators in 2012, and Batazzo and collaborators in 2013, both published in the Journal of High Energy Physics, used the measured Higgs mass to evaluate the stability of our vacuum. Their conclusion: it is most likely metastable, not absolutely stable, not obviously unstable, right at the edge. The reassuring part of those same calculations is that the predicted lifetime of our vacuum is vastly longer than the current age of the universe. So in practical terms, this is not a near-term threat. The unsettling part is what would happen if a quantum fluctuation, somewhere at some unimaginable moment, did nucleate a bubble of true vacuum. That bubble would expand outward at the speed of light. Inside it, the fundamental constants would be different. Atoms as we know them could not exist. And nothing could see it coming, because no warning signal can outrun light itself. Number 8. The Big Crunch. For most of the 20th century, this was the leading candidate for the end of the universe. The logic was straightforward: gravity is universal. If there is enough matter in the universe, its collective gravitational pull will eventually overcome the expansion set in motion by the Big Bang. The expansion slows, stops, reverses. Galaxies, previously moving apart, begin to fall toward one another. the process accelerates. Over hundreds of billions of years, galaxy clusters merge, stars collide. The cosmic microwave background, the faint afterglow of the Big Bang, today measured at a temperature of approximately 2.725 Kelvin, begins to heat up as the universe compresses. Eventually, every structure dissolves into a plasma of elementary particles. Then that too collapses. The Big Crunch ends in a singularity, a point of infinite density, the same kind of point the universe began from. The discovery of accelerating expansion in 1998 made the Big Crunch far less likely. The expansion is not slowing, it is accelerating. But the scenario is not entirely ruled out. If dark energy turns out not to be a cosmological constant, if it weakens enough over time, or even reverses sign, gravity could yet win. Number 7. The Big Bounce. What if the Big Crunch is not an end but a beginning? Loop quantum cosmology, a theoretical framework developed in part by Abhay Ashtekar at Pennsylvania State University, proposes that space itself is quantized. It has a minimum possible size. In a key 2006 paper in Physical Review Letters, Ashtekar, together with Thomas Pawlowski and Parampreet Singh, showed numerically that within their model, the singularity at the start of our universe is replaced by a bounce, a transition from a previously contracting universe into our expanding one. This model does not eliminate the end of our universe. It transforms it. Our universe ends in collapse, but from the perspective of whatever emerges, a new universe begins. Some versions of the framework allow this cycle to repeat indefinitely. Theorists have explored whether such a bounce might leave subtle traces in our cosmic microwave background. But as of 2023, comparisons with Planck satellite data have not turned up the predicted signature for a single past bounce. So as a model of the cyclic universe, it is not confirmed. But as a way of asking whether time itself has an absolute beginning, it is one of the most carefully developed alternatives we have. Number 6. The Black Hole Era. In the far future, physicists place this epoch beginning around 10 to the 40th years from now. Ordinary stars will no longer form. The raw material for star formation, clouds of hydrogen gas, will have been consumed. The last red dwarf stars will have burned out. What remains will be the cold remnants of dead stars, white dwarfs, neutron stars, eventually black dwarfs, the theoretical endpoint of white dwarfs that have cooled to background temperature, a process longer than the current age of the universe many times over and dominating everything: black holes. During the black hole era, black holes are the major actors in the universe. They merge. They grow. Occasionally, they collide with drifting stellar remnants. The universe during this period is not dark in the way we imagine darkness. It is colder than anything we currently measure, a fraction of a Kelvin above absolute zero. The only energy source is the faint thermal radiation predicted to leak from black holes themselves, Hawking radiation, derived by Stephen Hawking in a 1974 paper titled Black Hole Explosions. In the journal Nature, but never directly observed, the black hole era is not an ending. It is a vast, nearly featureless waiting room before the ending. Number 5. Heat death. The second law of thermodynamics states that in any closed system, entropy disorder increases over time. Energy flows from concentrated forms to dispersed forms. Heat flows from hot to cold. This has no known exceptions. No known mechanism reverses it. Extrapolated to the entire universe, which is, by definition, a closed system, this law predicts a final state, a state in which all energy has been evenly distributed. No temperature gradients remain. No chemical reactions can occur. No mechanical work can be done. The universe reaches thermal equilibrium. This state was called Wehrmacht heat death by the physicist Rudolf Clausius in the 1860s, when he first extended thermodynamic reasoning to cosmological scales. The endpoint is not hot. It is the same temperature everywhere. In a universe at perfect thermal equilibrium, time becomes a meaningless concept. There is no before or after because nothing changes. No clock can tick if no energy differential exists to drive it. The physicist Brian Greene devoted much of his 2020 book Until the End of Time to exactly this picture, the universe slowly settling into the most probable state allowed by physics, a state of maximum entropy from which nothing further can evolve. The remarkable thing is not that this will happen. It is that it is already happening, right now. Every star that burns is consuming irreplaceable ordered energy. We are watching it in slow motion. Number 4. The Big Freeze. Do not confuse this with heat death. They are related but distinct. Heat death describes a thermodynamic equilibrium. The Big Freeze describes what happens cosmologically as the universe continues to expand under dark energy. Even if all thermodynamic processes paused, the expansion of space itself would continue. Galaxies would recede beyond each other's observable horizons. Closer to home, the standard textbook picture has long been that the Milky Way and the Andromeda Galaxy are heading toward a merger. The resulting galaxy, sometimes called Milkomeda. But a 2025 study published in Nature Astronomy, using the latest data from the Gaia spacecraft and the Hubble telescope, and accounting for the gravitational pull of nearby galaxies like the Large Magellanic Cloud, found the merger is far less certain than once believed. The probability of a Milky Way and Andromeda merger over the next 10 billion years is now estimated at roughly 50%. Either way, in this scenario, the universe does not end explosively. It does not compress. It simply becomes unreachable to itself. Galaxy clusters will eventually be carried beyond each other's cosmological horizons. Every island of matter, separated by distances no force can ever bridge again, frozen in their own isolation. Number 3. The Big Slurp. This is the colloquial name some physicists have given to the most dramatic version of false vacuum collapse, popularized by Joseph Licken, a theoretical physicist at Fermilab, around 2013, in talks given after the Higgs boson mass was measured at the Large Hadron Collider. Licken's framing was philosophical as much as physical. Why, he asked, do we live in a universe that is sitting right at the edge of stability? Why not safely stable? Why not obviously unstable? The bubble of true vacuum, if it ever nucleated, would expand at the speed of light. Any point in the universe reached by it would not experience destruction in the conventional sense. The particles there would simply cease to be the particles that currently exist. New physical laws would govern whatever remained. There would be no warning. Importantly, the fact that our universe has already lived for 13.8 billion years, exposed to high-energy cosmic ray collisions in countless places, is itself strong evidence that the lifetime of our vacuum is enormous. Most estimates put it at trillions of years or far longer. But the unsettling philosophical residue of the Big Slurp remains. Whether any structure could persist inside a true vacuum bubble is unknown, because the physics inside it would be, by definition, physics we have never observed. Number 2. Black hole evaporation. In 1974, Stephen Hawking published a short paper in Nature with the deliberately provocative title, Black Hole Explosions. In it, he showed that black holes are not completely black. Quantum mechanical effects at the event horizon cause them to slowly emit thermal radiation, what became known as Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. For stellar mass black holes, the temperature is far below even the cosmic microwave background. So in our current universe, they absorb more than they emit. But in the far future, as the universe cools below the temperature of the cosmic microwave background, even stellar mass black holes will begin to net evaporate. The process is extraordinarily slow. Modern estimates put the evaporation time of a black hole with the mass of the Sun at roughly 10 to the 67th years. Supermassive black holes at the centers of galaxies, with billions of solar masses, would take on the order of 10 to the 100th years or longer. But eventually, every black hole evaporates. And when the last black hole is gone, the universe will contain only a thin, cold gas of photons and leptons, electrons, positrons, and neutrinos, drifting through an expanding void. The information paradox. What happens to the quantum information encoded in the matter that fell into the black hole remains one of the most contested open problems in theoretical physics. Number 1. The Big Rip. Every other scenario on this list is either unconfirmed or depends on conditions we cannot yet measure. The Big Rip is different. It is driven by dark energy, and dark energy is not theoretical. We have measured it. We observe its effects in the redshift of distant supernovae. The question is not whether dark energy exists. The question is what kind it is. If dark energy is a cosmological constant, a fixed property of space, the expansion accelerates at a steady rate, and the universe trends toward heat death or big freeze. But if dark energy is a different kind of field, what physicists call phantom energy, with an equation of state parameter W less than -1, then the acceleration itself accelerates. The expansion does not just carry galaxies apart. It begins to rip apart the structures that gravity had been holding together. The scenario was formalized in a 2003 paper in Physical Review Letters by Robert Caldwell of Dartmouth College, with Mark Kamiankowski and Nevin Weinberg of Caltech. Their calculation, for a sample value of W of -1.5, laid out the sequence. About 60 million years before the end, the Milky Way is torn apart. 3 months before the end, the solar system becomes gravitationally unbound. 30 minutes before the end, Earth itself disintegrates. Atoms come apart in the final fractions of a second. The metric of space tears. Now here is what makes this number 1. In 2024 and 2025, the Dark Energy Spectroscopic Instrument, a major sky survey based at Kitt Peak in Arizona, released measurements suggesting that dark energy may not be a constant after all. It may be evolving. Combined with supernova and cosmic microwave background data, the evidence points at over 3 sigma toward a model in which dark energy's equation of state has been changing over cosmic time. It is not yet a confirmation of phantom dark energy, but it is the first time the measurement has nudged the data in that direction. We are, quite literally, measuring the shape of our own ending, and the data is not yet precise enough to rule out the most violent answer. 10 scenarios, all of them scientifically grounded, all of them possible, none of them certain. The honest answer to the question of how the universe ends is that we do not yet know, because we do not yet know what dark energy is. That single unknown determines whether everything ends in slow thermal equilibrium, in accelerating isolation, or in violent, complete structural dissolution. What is remarkable is not the uncertainty. What is remarkable is that we can ask the question at all. We are matter that became complex enough to model its own end. We are the universe examining its own death. And the tools we use to do it, mathematics, observation, inference, are getting sharper every year. The James Webb Space Telescope is reshaping our view of the early universe. The Dark Energy Spectroscopic Instrument is, right now, returning the most detailed maps of cosmic expansion ever made. The European Space Agency's Euclid mission is mapping dark matter and dark energy across billions of light years. The answer may not be known in your lifetime. It may not be known in 100 lifetimes. But the question is being worked on, with seriousness, with precision, by people who understand that getting it right is one of the most consequential things our species has ever attempted to do. If you want to follow along the edge of what we know, subscribe. We will be here, watching the data.